Alright, I'm going to analyze the crap out of some functions here using calculus. So let's see, number 3. Use both the first and second derivative test to show that this function has a relative minimum at x equals 1. Okay, so let's see. First and second derivative tests, I guess I'm going to need the first and second derivatives, probably. Okay, so first derivative test, what is that? Well, the first derivative test is when you show that the derivative, let's see, make a little sign chart here. The sign chart is not the answer. I want to make this very clear. Some number of years back, the College Board made a great big production of letting calculus teachers know that these little sign charts that we like so much are not answers or justifications. You can't do this and expect that that means anything to somebody looking at your work. It's just a way of organizing things. So the first derivative test, we know that there's a minimum here because, so you'd say f of x has a minimum at x equals 1 because f prime of x goes negative to positive. That's what the first derivative test is. So it's basically your description. I mean, look, this is the words that say what the sign chart means, right? But you have to say the words. And believe me, there's plenty of assessment situations from me and the College Board eventually where you have to say this to get the credit. Okay, so what about the second derivative test? The second derivative test is showing that, first of all, f prime has to be 0. F prime of 1 is 0. That's true, and you plug 1 in there. And f double prime of 1 is 6. So here, the justification is, I say f of x has a minimum at x equals 1. Same so far, we're claiming the same thing, because f prime, because the derivative is 0, and the second derivative is positive. I just put a plus sign there. You can see the edge of the screen. There we go. So if we're thinking, like, what does this mean? Because the derivative is 0, that means I've got a slope of 0. And if it's concave up, then it has to be nestling above that, which would make that a minimum. Right? Here, the first derivative test, thinking about, like, what does this mean, what we said here, if the derivative, if you think about the derivative as the quantification of increasing or decreasing as we move from left to right, if it goes from decreasing to increasing, well, that's got to be a minimum there, right? So those are two different ways that you can justify. All right, let's do it again. Number 4, I've got the function sine squared of x. Oh, is there a b in this one? Well, you know what? All right, fine, I'll do it. I was going to say you can do that one yourself, but that's just not right. Bad example setting. The laziness almost got a grip of me. I shook it off. Okay, we're talking this time So here, let's see, I'm going to just reuse my columns here. So I'm going to make my little sine chart. They already told me that we're interested in x equals -1. Okay, so when I plug -1 in here, sure enough it's 0. If I go on the other side of this, plug in like -2, that's going to be that's positive. And if I plug in 2, I'm supposed to be doing x equals 1 and -1. All right. So I guess I'll do -1 first. So when I plug in a number less than -1, then like -2, that gives me a positive number. And if I plug in a number that's a little bit bigger than -1, like 0, I get a negative. Sorry, that's a mistake there. There we go. Okay, so I can say f of x. Oh, you know what? I'll do these on the same sign chart. And let's make this 1. They also asked about 1. Then it goes back to positive again. So I can say f of x has a, here, this would be increasing and then decreasing. So that's a maximum at x equals -1 because f prime goes from positive to negative, always reading left to right. And while I'm at it, f of x has a minimum at x equals 1 because f prime goes from negative to positive. If you're thinking to yourself, whoa, you're abbreviating a lot of stuff here, Mr. McGrath, this is fine. I'm all for you abbreviating things like this. That is fine. The magic words are that f prime goes from positive to negative or vice versa. That's what must be said. So that is that. Now I want to use the second derivative test. So here, f of x has a maximum at x equals -1 because, so for the second derivative test I want to show that this is 0 because f prime of -1 is 0, sure enough, and the second derivative at -1 is negative. So if it's concave down, that's got to be a maximum there. And f of x likewise has a minimum at x equals +1 because f prime of 1 is 0 and f double prime of 1 is positive. So positive, if you're concave up, that goes with minimum. Maybe that's a tiny bit counterintuitive that like positive is a minimum, but when you're doing that second derivative test, if you just think about the picture, that should jive with your intuitions just fine. All right. So one just comment about all this is that, and that was all number 3, not number 4 yet. Yay. That the first derivative test, there's only one thing to say. It's got a minimum because this. And the second derivative test, there's 2 things you have to say. You have to say that the derivative is 0 and whatever the sign of the second derivative. Right, there's 2 things. One thing, 2 things. Look at that. All right, number 4. Use both tests to show that sine squared x has a relative minimum at x equals 0. And we're going to do the same thing for tangent squared. So sine squared x, better to write it like that. That's 2 sine x cosine x times the derivative of what's inside, right? Chain rule. If you remember your trig identities, that's the same. That's the sine. That's the double angle formula for the sine function. That's sine of 2x. You don't have to remember that, but if you do, it makes finding the second derivative a little bit neater. So sine of whatever, derivative is cosine of whatever, times the derivative of what's inside. That's just a little easier to deal with. So I'm going to work with that version because I remembered my trig identities. And we want to show that it's got a relative minimum at x equals 0. So let's see what the signs are doing here. So sine of 2x, that's going to be negative on this side and positive on this side. Test some values if you like. So I'm going to say that f prime, I'm going to say that f of x has a minimum at x equals 0 because f prime of x goes from negative to positive. It's got to be a minimum. And the second derivative test, I'm going to say the same thing. F of x, I don't know why I made that line there, has a minimum at x equals 0 because f prime of 0 is equal to 0 and f double prime of x is equal to 2, which is positive. So that's got to be a minimum, right? Okay, that was part A. Part B, they want the same thing done for f of x is equal to tangent of x squared. F prime of x would therefore be 2 tangent x times the derivative of what's inside. That's secant squared x. Well, I don't think there's any trig identities going to help me here. I just have to do my product rule. So I'm going to consider this to be the first and this to be the second. So the derivative of the first is 2 secant squared x times the second plus the first times the derivative of the second. Derivative of the second would be 2 secant x, because that's something to the second power, times the derivative of what's inside. Derivative of secant is secant tangent. You don't have to simplify things, but when it's when you're going to do something with it, then it's often beneficial to do that. So that's 2 secant to the fourth x plus 4 secant squared tangent squared. I think I'm okay there. That was fun. So how about sign chart at 0? So let's see, the secant squared, this is always going to be positive. It's something squared. So the tangent function goes from negative to positive. Right? So that means that f of x has a minimum, decreasing, increasing, at x equals 0 because f of x goes from negative to positive. Second derivative test, f of x has a minimum at x equals 0 because f prime of x, f prime of 0 rather, is 0. Is that true? Yes, tangent of 0 is 0, so it doesn't matter what this is. And f double prime of 0 is, all right, let's see. This has a tangent in it, so that's going to be 0, because tangent of 0 is 0. And secant of 0 is like cosine of 0, which is 1, upside down, which is 1 times 2, so that is positive. So there we go. That's a lot for those little 3 and 4. Yikes. And then what about part C? Give an informal verbal argument to explain without calculus why the functions in part A and B have relative minima at x equals 0. I don't know exactly what you would want to say, but you could say something like, if this is the tangent function, if the tangent function looks like this, then tangent squared is going to take all these negative values and flip them up. So all the stuff that was negative is going to get flipped up. So that has to be a minimum there. I think that's what they're on about. And then what about the graph of the secant function? The graph of the secant function is, if you can picture where the cosine function is, it's like the cosine function, but all the bits are getting like flipped. Right, like as the cosine function does this. The zeros, when you turn those upside down, turn into infinities. And you get these little bits that look like this. Now those are all positive. Of course, 1 squared is 1, and anything bigger than 1, when you square that, it's going to get bigger. So when you square that, f of x, you're just going to get something that looks an awful lot like that. It's just going to make it kind of like steeper in there, but the minimum is going to be in the same spot. So I think that's what they're just reminding you. You know, you can think about the functions that you know and know stuff about them. All right, first 2 problems done. Let's see if these ones go faster. I think they will. 7. We want to locate the critical points and justify which critical points are stationary points. Okay, so point of order here. What's a critical point? You have this in your notes, but I'm just going to remind you. Critical point is the derivative is 0 or undefined. Right? So a critical point is a place where the derivative is 0 or undefined. So there can be, like, you know, the pointy part of an absolute value graph. That's a critical point, but the derivative is not 0. It's undefined. So if you're out there in the world of functions hunting for maximums and minimums, you should consider not just places where the derivative is 0, you should also consider places where it might be undefined. Those can also be maximums and minimums, just like the pointy part of an absolute value graph is a minimum. And a stationary point, this is some vocab that our book uses. I don't really use it much. College Board doesn't use it. Stationary point is like a well-behaved critical point. That's where the derivative actually is 0. Why would you call it a stationary point? Well, if you're thinking about the context of position versus time and the derivative of that, then the derivative of position is velocity. So places where the derivative is 0 are like places where the velocity is 0, so you could think of it as a stationary point. That's what motivates that vocabulary there, or that choice of word. All right, so I've got here in number 7, f of x is equal to 4x to the 4th minus 16x squared plus 17. And I'm trying to find critical points. That's where derivative is 0 or undefined, and then just make sure I know which is which. That's all. So f prime of x is 16x to the 3rd minus 32x, and I'm going to set that equal to 0. And factor, because that's what you do. So it looks like I have critical points at x equals 0 and plus or minus the square root of 2, and they're all stationary points. All right. Number 9, got f of x is equal to x plus 1 over x squared plus 3. The derivative is low d high is 1 minus high d low over low, but just looking forward to what's happening here. This isn't going to matter for me because I want to know where this is equal to 0, and a fraction is only equal to 0 when the top's equal to 0. So there you go. So let's set that equal to 0, just the top. Let's see, x squared minus 2x squared. 3, no constant there. And minus 2x. So let's rearrange that. That factors. So x equals negative 3 and 1. And those are both stationary points. Because you can go back and check. See, do they make the derivative equal to 0? Yep, they sure do. 11. How about the cube root of x squared minus 25? Derivative would be that. Okay, so let's try to clean this up a little bit. So this would be on the top. I'm going to put the 3 on the bottom. And then I'm going to rewrite this back in radical form so I can kind of get my head around what's going on here. It's the cube root of x squared minus 25 squared. Okay, so when I'm looking for critical points, here I didn't have to worry about that being 0 because x squared plus 3 is always a positive number and it's getting squared. So this is never equal to 0. What about this? This is a little bit different situation here. So the other thing about this, when you use the quotient rule, the thing that shows up on the bottom here, the low, it's the low. It's the same, it's a version of, it's just this thing squared. So if there was something that made this equal to 0, it would have also made this equal to 0. And if it's equal to 0 here, that means that at that value of x, there was no point on the original function. It would be some version of undefined, right? Let me say that again. All the places that make x squared plus that make the denominator of a rational function equal to 0 of the original function are, because of the way the quotient rule works, obviously going to be places where the derivative is undefined. Is that a critical point? No. Why not? Because it's not even a point. It can't be a critical point if there isn't even a point there to begin with. Right? You could say it's a critical value, I guess. It's a place where the function has a domain issue, right? But it's not going to be a critical point because the derivative doesn't even exist there at all, right? There's no point to talk about. Now this, functions to the fractional powers, especially fractional powers with odd numbers on the bottom, famously have this kind of property where you end up with a denominator in the derivative where you didn't have a denominator here. Like, what are the kinds of numbers that you can raise to the 1/3 power? You can raise anything to the 1/3 power. Positive, negative, 0. You can take cube roots of everything. So this is good. This function does not have any domain issues, but its derivative does. So when we look here, my critical points are going to be anything that makes the denominator 0, numerator, and then also anything that makes the denominator 0. So that's going to be plus or minus 5. The 0 is the stationary point, and these two are undefined. If you want to see what that function looks like, go ahead and graph it in your calculator, and you'd start to get an idea, like what does it mean for a function to have a point, but for the derivative to be undefined there. I think that's probably a good idea to do that. All right, last one of these. How about the absolute value of the sine function? Is the derivative of that the absolute value of the cosine function? No. We do not have any rules for taking derivatives of absolute values of things. You just have to think. Sorry about that. So, what does the sine function look like? Looks like this. What does the absolute value of the sine function look like? Well, the absolute value of the sine function, all those things are going to get flipped up. So you get a bunch of bumps like that, all into positive territory. Now, all of these are critical points where f prime is undefined, and all of these are stationary points. We could say. I was going to say critical points where f prime is 0, but since we're using this vocabulary right now, those are stationary points. So you can list out the answers if you want. These are all at multiples of pi, and these are all at multiples of half a pi. All right. I'm sorry, that's not true. They're not at multiples of half pi. They're all at odd halves of pi's. Would be the right way to say that. Okay, where are we at here? We have done 7 to 13, so 15 through 18. Sorry, last stretch here. Uh-oh, I might be out of paper. Hold on one second. So 15 through 18, these look like little graphs to look at. Not too bad. Use the graph of f prime shown in the figure to estimate all values of x where there's minimum, maximum, and inflection points. Now these are graphs of derivatives. This is a really important thing for us to be able to do, to look at the graph of a derivative and say what we can say from that. So this is the graph of a derivative. So the slopes of this, not the slope of this, but the slopes of the original function of f are positive, and then they're negative. And this is at 1 right here. So f prime has a maximum at x equals 1. Why? Because f prime goes from being positive numbers to negative numbers. That's it, and that's the only place where it crosses. So that is the only, there's a maximum, no minimums. What about inflection points? An inflection point is where the second derivative changes sign. So that would be, let's think about how we would locate that on a graph of the derivative. If you want the second derivative, which is the slope of this, if you want that to change sign, that means this graph would have to have a maximum or a minimum. The slopes of this would have to change from positive to negative or from negative to positive. And this does not have any maximums and minimums, so there are no inflection points. So max, min of f prime graph, those are inflection points. All right. how about this? 1, 2, 3. So what's going on here? I have, this is a graph of the derivative. So places where it crosses, those are going to be maximums and minimums. F prime has this is negative to positive, has a minimum at x equals 1 because F has, oh dear. So I'm making claims about the original function, right? Sorry about that. F has a minimum at x equals 1 because F prime goes from negative to positive. F has a maximum at x equals 3 because it goes from positive values to negative values. That's increasing to decreasing. Because F prime goes positive to negative, and F has an inflection point at x equals 2 because the second derivative, which is the slope of the first derivative, so those slopes go from being positive to negative. And you can say, because it's an inflection point, we're not saying whether, it doesn't matter if it's going positive to negative or negative to positive. You can just say because F double prime changes sign. I'm going to be more specific right there. Number 17, you're looking at the graph, so I'm not going to recopy it. I'm just going to say that F has a maximum at x equals 0 because F prime, which is what we're looking at, goes positive to negative. F has a minimum at x equals 2 because F prime goes from negative to positive. And F has inflection points at x equals 1 and 3 because F double prime, which is the slope of F prime, changes sign there. All right. Last one. Number 18, you know the drill. F has, what about this thing at -1? What's going on there? Is that a maximum or a minimum? It's kind of like it's trying to be, but it doesn't cross, so it does not change sign. What would the original function look like there? Well, the original function there would be decreasing, and then the slopes are coming in to be 0, and then you wanted it to be, it was like trying to have a minimum, but then the slope started to get more negative again. So there is a place where it's equal to 0, but the original function would look like this. So that is not a maximum or a minimum, and that's what they're asking for. So not either one. Right? They didn't say find the critical points. They just said maximums and minimums. So F has, let's see, where's the first point where it actually crosses at 1? Has a minimum at x equals 1 because F prime goes from negative to positive, and F has a maximum at x equals, looks like x equals 3. Nope, just kidding. That's I'm looking for places where it crosses. That's going to be the inflection point at x equals 3, or one of them. at x equals 5 because f prime goes from positive to negative, and f has inflection points at x equals -1, 0, and 3, because f double prime, which is the slope of f prime, in other words, the slope of the actual graph we're looking at, changes sign there. All done.